Alright, welcome back again to High Score Online School. In our previous video, we talked about the energy stores and the energy transfers as they are required for Gcse physics specification for AQA. In this particular video, we looking into three energies which include kinetic energy, gravitational potential energy, and elastic potential energy, EPE. Alright, let's dive in. So in the last video, we introduced the concept of kinetic energy and explained to you that this is energy possessed by a body by the virtue of its speed. And speed is always gained or possessed whenever there is a motion. Yes, if there is a motion, there is speed. So the kinetic energy is energy possessed whenever a body is in motion, and the main concept, the main idea or the main parameter that determines the size of Ke is the speed. And mathematically the formula is kinetic energy is always equal to 1 over 0.5 multiplied by the mass multiplied by the speed squared, the speed all squared. Hence, the higher the speed, the higher the kinetic energy of that body. For example, a moving vehicle. So this is the formula for kinetic energy of a body. Now, for some questions, for Gcse questions, we may be asked to tell what happens. What happens when we double the mass? If we double the mass, so if we double the mass, what happens to the energy? Double the mass, what happens to the energy? Let's find out. If the energy is given as energy, initial energy is E1, let's use this. Initial energy is E1 equal to 0.5 mv squared. So if we double this mass so that m2 becomes 2 times initial mass m. If we replace it with here, we have that final energy after the mass is doubled, going to be having 0.5 times, take away this, put this, times 2m v squared. And of course, 0.5 times 2 is simply m, to give us m v squared. This is what we have as E2. And if we take the ratio of E2 over E1, that will give us m v squared divided by E1 is 0.5 m v squared. This will cancel this, and we are left with 1 all over 0.5, which is equal to 1 over 1 times 0.5 is, okay, 1 over 1 times 2 over 1, which is equal to 2. Automatically, it simply means that if the mass is doubled, the final speed, the final energy is twice initial energy. Therefore, if we double the mass, energy will be doubled also. Double the mass, energy is doubled. All right, so that's what happens there. Now, what if we double the speed? Okay, if we double the speed, remember we said the initial energy E1 is is 0.5 mv squared. So if we double the speed, that means that E2 will be equal to 0.5 m into 2 times this, that is 2v all squared. This will give us 0.5 m, opening bracket, we have 2 squared is 4, v squared remains v squared. That will give us 0.5 times 4 mv squared. 0.5 times 4 is 2. That is 2 mv squared. If we take the ratio of E2 over E1, that would be 2 mv squared all over 0.4 no please all over E1 is 0.5 mv squared. Cancel this and cancel this. We are left with 2 over 0.5, which is equal to 4. So that means when we double, if we double the speed, then it becomes 4 times. E becomes 4 times. All right. However, a question may come asking us to find out what happens if we double both the energy, if we double mass and speed, what happens? Initial energy E1 is 0.5 mv squared. If we double the mass, E2 becomes 0.5 times, mass becomes 2 times m. 2m times 2v all squared. This will be 0.5 times 2 is 1 times, this is just 1m, which is m, times 2 squared is 4, v squared, yes, equals 4 mv squared. So if we take the ratio of E1 upon E2, E2 upon E1, please. E2 is 4 mv squared all over 0.5 mv squared. This cancels this and we are left with 8. So if we double both the mass and the speed, the kinetic energy is going to become 8 times the initial value. All right, let's go to the next one. The next one is gravitational potential energy. Gravitational potential energy. Gravitational. Okay, initially we said this is energy possessed by a body by the virtue of its position relation to the ground. If we have this as the ground, this is the ground level, and a body is placed here. This body is being placed here. Okay, if this body is to be taken up from here now to this place, yes, this particular one here has no potential energy. GPE is 0 because the height is 0, but this particular one here, the height is h. So this one now, if it's being released to fall to the ground, is going to do some work on anybody it meets. So the GPE is proportional proportional to the height at constant width. So GPE is equal to width times height, and of course weight is equal to the mass times gravitational field intensity, G, gravitational intensity, times the height. So that is mgh. M is in kilogram, kg. G is in Newton per kilogram or meter per second squared, and H is in meters. Sometimes may be given the problem in grams. To convert grams to kilogram, simply divide by 1,000. So that's how we calculate the gravitational potential energy. Let's go to elastic potential energy. Elastic potential energy is the elastic potential energy is simply the energy stored by a body when it is being stretched or when it is being compressed. If I have this, let's assume I have this spring. This is a spring. Sorry. A spring. Now, if I apply a force this way, upward, this way, and this way, downwards, this spring is going to have a stretch, going to stretch and become longer, such that this place to this place becomes the extension made, that has been extended by extension E. However, if the spring is being compressed, this spring can end up being something like this. It still remains that the compression still remains E. And if any of this is being released, it has the potential of doing some work on anybody it meets. So the amount of work done, it depends on the extension made and as well as the force of either compression or extension. All right, the elastic potential energy, EPE is always equal to 0.5 multiplied by the force of compression or extension times the extension. Yes, extension. That is 0.5 times F times E. Or you can also say it is equal to 0.5 times elastic constant, which is K, multiplied by extension squared. Of course, we should not be surprised. This and this are basically the same because both of them are coined from Hooke's law. From Hooke's law, F is equal to Ke. So if we replace Ke in this place now, we're going to be having 0.5 times F take away Ke times E. This still gives us 0.5 Ke squared. So this is exactly how we get the formulas for the energies. In the next episode, we'll be talking about how to solve problems with these formulas. And until coming away next time, thank you.